Hello everybody, today we will be continuing with dynamic programming stuff, but at first let me ask about the question that I asked the last time. Konstantin, did you solve the issue? Konstantin?
Yeah.
So we had this algorithm that checks whether one sequence is a subsequence of another sequence, and you come up with the algorithm where, like, you are coming, so you have start there, 0 then for E1 to as do, for G start T do if Si equals Tj, then break. Oh, sorry. Look at that. It was like start equals J plus 1, break, and that's all. That's kind of, as far as I remember, this is exactly the algorithm that you presented the last time, how to check that as subsequence of T. So, and I posed the question, what is the complexity of this algorithm? So, did you find out what is the complexity of this algorithm?
S plus T.
Yeah. Yeah, it is S plus T. Please note that J, like, you have one iterator that goes by the string S, and another iterator J that goes by string T. So J in their second loop, J only moves forward. It never moves backwards. So it only increases by 1. So if we state here like start, so this is start, and then the next start will be the next position where we stopped previous. So it will be start plus 1. So we start from here. So in total, their counter J will be going T positions to the right only. So that is why you have their complexity or linear complexity depending on the types. Because like the last time we had the problem to calculating the complexity of this, and there were lots of different versions, but the one is the right one where their complexity is linear. So let me continue then with dynamic programming. So we are coming already the third lecture on it. I don't know if we will finish today. I'm not 100% sure, but we'll try to do that. So the first question that I wanted to talk with you about is still the dynamic programming on the segments. So the last time we solved the problem where you are given a sequence of brackets and you want to get the subsequence of these brackets so that this subsequence will be the correct one. So this time you're given n matrices. So it is x1 times x2, this x2 times x3, etc. And this one will be xn times xn plus 1. So these are the matrices and these are the dimensions. So this is like the dimension of the first matrix is x1 times x2, the dimension of the second matrix is x2 times x3, and etc. And you know that to multiply two matrices of these sizes, it costs you x, y, z. So, and the question, suppose that we know that the total complexity of the multiplication of two matrices is x, y, z without O. And the question is, you're asked to calculate the multiplication of these matrices in their fastest possible time. So you know that the multiplication of the matrices is, for these two sizes, is x, y, z, and then you want to multiply the matrices in some order so that we can improve their total number of iterations. Is it clear, the problem?
Yeah, it's clear.
Okay, good. So let us
We
think.
have to define the order, how to...
Yeah, you have to define the order in which order you should multiply matrices. Because, like, for example, if you have matrix A, B, C, D, you can, for example, multiply B, C together, then multiply with A, and then you will multiply them together. So the order is not necessarily to be from left to right, it can be in some other order. A small hint, this is the problem on the dynamic programming on segments, as we talked the last time with the brackets. It should be applied also here.
As far as I remember, we have to split the task for some kind of subtask. We have to define some, let's say, variable like k between two matrices and calculate. Calculate this multiplication step by step.
No, I'm not following. Sorry. Can you repeat?
Yeah. I'm just trying to revise it because.
So yeah. So there. So the dynamic programming on segments, it is the same dynamic programming as usual, while the state is a segment from I to J. So we will calculate the dynamic programming. The minimal number of operations to multiply AI, AJ. Because it is obvious that the matrices can be applied only, like, you can multiply only the neighboring matrices. So it is reasonable to look at the segments. So how many operations should we perform when we multiply these matrices in some order? So the state is ij. How to recalculate this dynamic programming over the smaller ones?
We have to split this range from I to j for two ranges. Let's say I to n and from n to j or something like that.
I will choose k if you don't mind.
Okay. Yes, it can be k.
Okay.
And then we have to calculate how many operations we have to perform to multiply matrices AI to AK.
Okay, so we know this. We already know this, so we know this.
Yeah, and AK to AJ.
Okay. Yes. So and
after that we have to plus it, and for each this part we can also split it to once again.
yeah, but like this is almost fine. But when you split by k, you know that you should calculate for the left. You should calculate for the right. You already calculated that. But how to merge them together? So you know that
we should plus the number of operation which we have to perform to multiply these two matrices, and
okay. So what will be the dimensions of this matrix?
I to
it will be xi times
xi and yk.
Yeah, to be more precise, xk plus 1, and here xk plus 1 times xj plus 1. Yeah, so you have to add this thing. Yeah, so how to get the multiplication of the segment? As Ekaterina proposed, that we can get the multiplication of the whole segment as the multiplication of some left part and some right part. And then we should union these two matrices that we get from here to here, as we know exactly what other matrices will be there, what are their dimensions will be. So we simply multiply the corresponding dimensions and add this to here. So and we need to check all their possible split points. So you traverse from I to j minus 1. Obviously, you should set up their the base for this problem as for dp I is equals to 0, because to multiply their elements from ith to ith, it costs us nothing. And you should you should calculate in the following manner, that at first you traverse over length, like their outer like the length of the segment, and then by the position of the start. So at first you kind of calculate the answer for the segments of length 1, then for length 2, then for length 3, and etc. and so on, and for the length n. Okay. Is it clear? Are there any questions? Okay. The next problem that we are going to talk about is the knapsack problem. So you're given several items with different weights. Weight 1, weight 2, weight n. And you know that you have a knapsack that can withhold elements of the total weight m. The problem is, what is the maximal weight we can obtain with these elements, but still can withhold m? So we want to maximize ik, w1 plus wik, such that so you want to find some subset of the elements, so it will have their maximal weight, maximal possible weight, but at the same time it should be less than m. The thing that this problem is NP complete, to be more precise, but sometimes it can be solved if we're given some constraints for that problem. For example, we will talk about how to do that and in n times m time. So if we know that the maximal capacity of the knapsack is m, then we can calculate this problem like kind of in reasonable time. So how to solve it? Let us maintain the following dynamic programming. Where at first I and the weight w, which is Boolean. Can we choose a subset of first n elements so that their weight with the weight m, oh sorry, not m, excuse me, w. So suppose that we calculated already for the smaller, for all the prefix of I. So everything where I is less than k, we already calculated it. Sorry. Less than k. And we want to add the new element here. Let us go over all previous level, kind of. If you calculate this, if you think this as a table, so it will be 1, 2, blah 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 blah, k minus 1k, and here is 0w. Of course, for the first element, it will be 0 as true and weight 1 as true also. Everything else is false. So, right now, suppose that we calculated everything up We calculated everything up there, and we want to add a new element. So we have two options there. We have either to add a new element or not to add the new element. So we go over all possible values for, oh sorry, yeah, I did a little mistake here, so it is not W, it is M. So we traverse over 0 to M and ask, we either do nothing, so dp equals dp or dpk times W, or dp k minus 1 W. This means that we do not take the element. So this means that we simply go to the next line. Or we should tell dp k W plus wk equals to dp k W plus wk, or dp k minus 1 W. So we have two options here. We either do not add a new element, or we add a new element there. And then how to get the answer? The answer, we simply should take their minimum such that dp of n0 m is true. Oh, sorry, maximum. That's all for this problem. So we will now go further. Are there any questions about how to calculate that?
I'm sorry, I don't know. Maybe you can actually give us some description on things discussed before lecture, so we could see before, and then you could come and maybe moving a little bit more from us.
Okay, that's kind of different question.
I know, sorry, that's why I did like it.
Yeah, but like, do I understand that or you don't? The question right now is pretty simple. Okay, I understand what you're trying to tell me so that you can read it and then you can answer it. No, just now I'm not asking from you anything. I'm just asking whether you understood what I explained right now or not.
No, I think more or less.
Okay, but I hope that further it will be a little bit easier. So right now we want to calculate, so we have each element has cost right now. And you want to calculate not their maximal weight that can be fit, but the maximal cost that can be fit in a knapsack. So you want to calculate, find such a subset of the elements so that their cost is the maximal possible, but at the same time it's still fit into their knapsack. So now dynamic programming will be a little bit different. So not can we choose, but the minimal cost of a sum of the subset of elements 1 blah 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 I with the weight W. So now instead of true false, we will maintain what is their maximal cost can we obtain if we take the first I elements and their sum is W. You even do not expect that this thing will be exactly the same here, but not with OR, but with maximum. So it is either maximum dp k v or dp k minus 1v. This means that we do not take an element. Otherwise, it is max dp k w plus wk with dp k minus 1 w plus ck, where k is the element that we're going to add. So we either take either we do not take an element, then the maximal for the first elements from 1 to k is the same as only elements from 1 to k minus 1. And if we decide to add new element, then you just simply compare the best answer with their answer that we take the weight for the first k minus 1 elements and we pay cost, we get a cost ck. That's it. That's what you need to know about knapsack problem itself. Okay, small mind breaking exercise. Suppose that right now we have not the elements, but the types of elements. So we can get how many we want of elements of the first type, how many we want the elements of the second type, blah, 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 and how many elements of their nth type. So right now we are not bounded with one element per the type. Right now we can do any number of elements of the same type. How we should change the program a little bit so it will calculate what we want at the same time.
So we not only take like this into SAC and have a program very cost, but also the right time.
Yeah, so you can add like one element of type 1, 2 elements of one type from the first type, 3 elements of first type, like how many do you want? So instead of the elements as itself, you know the types of the elements.
Okay. but we still have cost because that now sounds like capacity is the cost line function. So
No, we still solve the same problem, but instead of a subset, here will be multiset. Was this the question, or the question was a little bit different? So like for the problem here, so we have tk, where I choose not I by type, but type, so we know k elements of some types. Okay, if it's not clear, let me do this. So at first we will copy all the information from the previous level. So what is their maximal cost can be for if we take the elements only of the first k types with exact weight w. So we just simply copy from the previous, so like as we do not take element k. Then we go for w from 0 to m, and we simply say that dp of k, so we will have exactly the same thing here, max dp k plus wk, dp k w plus ck. Please note that previously in the previous algorithm we know that we add a new element, so it was here like -1 here. So you know that either you take an element, like either you do not take the element, or either you take the element. But here we know that we can add any number of elements. So we can simply say here from k, and this is kind of, we are going from the left by this line, from the left to the right, and trying to add an element to any possible weight. So, and by this time we can add our element several times because we are coming through the same line. Kind of, we can have like add here, and then when we come over this element we can add here. So we add this several times. So that's it. Questions? Okay. Is it complicated, or like you understood everything?
It's a bit complicated.
It's a bit complicated. What is the main issue that you're stuck with?
is there a reason? Okay, I might be know the reason. but it's not because sometimes you write code and the symbol and you do understand what it is doing, and sometimes you looking at things and you try looking for what you are talking, so it should be clear, but it's not the well.
So, do you understand what dynamic programming are we calculating? Like the idea, what is dpiw?
Yeah.
It is clear.
That's,
Okay, if you understand this, what is dynamic programming? The question is how to recalculate it. Do you understand how to recalculate it for the standard knapsack problem where we had n items and different items?
no, we just choosing that bring the action that brings us more work.
Yeah, so we have this action, either we took element or we do not. And that's you simply recalculate. I mean, probably their thing with the pseudocode is not very clear, but their idea is that you have two options, either to take an element or not, and you check both of them. So it was like that. Here it was -1. This is how you calculate for the knapsack problem. So this is you do not take an element, this is you take an element. Here you can see that. I had the weight plus the weight of the element here. And here I ask what was the previous maximal cost that we could get is the first k-1 element with the weight w plus the cost of the kith element that we added. And we take the maximum out of them. Either we should be the same or we should replace with the better answer. With the types of the elements, we can simply erase this -1 and everything will be working perfectly fine. If it's not clear why, let me take this, give you this as a homework to understand why it is true. If it's not clear, because like I'm not sure that I'm able to explain to you in any other way. I have no idea. It is just simply like by this thing is that you either add an element, and then since you come over this weight again, you add an element the second time. Okay, so you know that okay, the question is, do you understand how to restore the subset? So you want to calculate the standard knapsack problem where it had here k-1 w plus ck. And you're asked to return the subset that achieves this goal. Do you understand how to restore it? Like what additionally should you store there?
We should store an action because we have enough that we are moving, and we are moving for n plus k or k n plus k or k minus k, and this one. This one.
Yeah, that's true.
So we
okay, yeah. So we just stored the action on how we got to this element, and like either there are two versions, right? Either we took an element or either we don't take an element. And then you simply go.
Also, sorry.
Yeah, what also?
I mean, if we have an alpha in the rewards calculated, we can just check in the same matrix that we've been there. If you don't want to return.
How do you check in the matrix? Like, can you repeat, please?
I'm not sure, but if we use this private graph, because I was thinking we have a matrix with the walls.
Yeah, we have the matrix with the values.
So when we recall it, or we also can check so we recognize max of the function, and we just also know in our matrix.
Yeah, you could restore it without anything. You just for each position check either you get from here or you get from somewhere here. Yeah, you can do that. You do not need to store anything at all. Okay. I hope that you will be able to write the code for this. It is not very hard. Okay, another question. While I'm trying to erase everything from the board, the question is the following. What is the memory complexity of the algorithm? So how much memory do we have?
We are using now?
Yeah, how much we are using right now memory?
So on the table it's going to be its length and width. On the time.
Yeah, so it is n times m also. So the question, suppose that we are asked not to restore the result, like the subset, but you just want to calculate the result, and that's all. Please tell me how to reduce the memory complexity to just O of m. Oh, sorry.
We can calculate your work each step, not looking in the matrix.
What we can calculate?
Calculate your work each time.
Can you repeat, sorry? What do you calculate each time?
The reward.
The reward each time.
Well, I'm not sure. How is the feeling you in the matrix beforehand?
How we fill the matrix beforehand? It is just simply you just put for the 0 and W1 here, like 0, 0 and constant I, and for everything else is minus infinity. Is this the question that you asked?
Okay, I think so.
So this is how you set up their whole matrix. Okay, let me then explain and we will move forward. So the thing is that, as you could see on the algorithm, is that when you add the element k, you only want the answer for the first k minus 1 element. So you kind of took. If you want to recalculate for the k, you just simply calculate it from the previous row. And you do not care about the rows that are later, that were late. So you just simply can store the last two layers, and then you kind of, when you come to the next, you reinitialize whole array, and like then you calculate for k plus 1.
Okay. So we have length of our array of things, and we have types of things on
It doesn't matter types or the elements itself.
Yeah, it doesn't matter. I'm just saying it's so when you check for the item, just choose one of the ways, and so we are interested in the next one and in the previous one.
Yeah, exactly.
Sorry.
Okay. Now we will come for a different side of the problem, from the different angle. And suppose that you're again given elements with the weight 1, like cost 1, weight 2, cost 2, and etc., weight n, cost n. But the weight itself can be very large, so up to 10 to the power of 9, for example. In the previous problem, we used the fact that the capacity of the knapsack is somewhat very small because our complexity depended on of n and of m. So if m was not very huge, then we could calculate that problem in reasonable time. But what if the capacity is also very huge? The only thing that can save us here is to calculate all the, iterate through all the possible subsets of the elements. Through all the subsets. How to do that? I will show you the code right now on how to do that. And we will see, but unfortunately it is mostly on C++ or Java, not for the Python. So for the Python you have to think a little bit to transfer the code. So you want to calculate the answer, which is at start is 0. Then you come for mask, which is from 0 to 1 minus 1. So that's how we iterate over all the subsets. So this is 2 in the power of n. So we iterate our mask from 0 to 2 in the power of n minus 1. So this is 2 in the power, like this together is 2 in the power of n minus 1. So this shift, this means that we took 1 and multiplied n times by 2. So it's like the binary, you could consider it as a binary string. Like you should think right now about it as a binary string. So then we go, so we have current, weight 0, current, cost 0. So we come for all elements j to n minus 1. we want to check whether J lies in this subset or doesn't lie in the subset. For that, you could take if mask and 1 over J and 1 bigger than 0, then for W plus equals WJ, for C plus equals to CJ, and finally if for W less than M, we take answer max ans for C. So here is, like, again, we go over all the possible subsets which are 2 in the power of n. As you know, either you take an element or you do not take an element. And then you want to understand from each element whether it lies in this subset or not. To check that, you just simply take your mask and with the binary, oh sorry, end it in a binary manner with J. So it is like this thing kind of will be 0, 1, 1, 0, 1, and this will be 0, 1, 0, 0, for example, if J is 3. No, if J is 2, sorry. If J is 2, so like this is bit string will be 1, 0, 0, this bit string is 0, 1, 0, 1, 0, 1, 1, 0, 1, and you check whether their end is bigger than 0. This means that is this one is at the place, and if it's in the place, by meaning that it is bigger than 0, we add the weights and their cost here. Okay?
No? Sorry, usually we use this binary addition when we have same name for. So we just do we compare against the last digits of the first one and what's in this just.
Sorry, can you repeat that? I will come closer.
So would be the answer is that we compare the last three digits of the binary string. The first one is like 0 or 1 and 0 to in 100. So it's 1 and 1 1 and it's 0.
Typically you can transfer mask to the binary string and like get everything you want. You just go over the string and check whether the corresponding character is 1 or 0. You can do that. Was this a question or I didn't understand the question?
No, it's okay, sorry.
So yeah, you just can you just ask for integer dot binary string or something and then just go over. I mean, I'm writing this because it's the simplest way to calculate, because this multiplication by 2 costs very small amount. It is very easy for the computer to shift the bits to the left. So this thing means that it's simply just multiplied by 2 in the power of something. Like just shift all the bits by G positions to the left. Okay. So if you understand that, so this is simply we just traverse over all subsets. So the next question. Okay, what is the complexity of this algorithm? Can you tell me?
Okay, there are two loops. It should be worst case of n squared, and that's how I'm saying.
Why n squared? Like, what is this? So it's 2 in the power of n. Their outer and cycle is 2 in the power of n.
So inner cycle is 2 power of n, and no, outer cycle, and inner cycle is n.
Yeah. Yeah, so like kind of you just multiply this and you will get their complexity.
Yes, I'm saying.
Yeah, so it is n times 2 in the power of n. Like there is nothing very hard here. Okay. Boom, 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 boom. Sorry. У меня пара перезвонил. Okay. I'm thinking whether we want some kind of advanced material or we do not. I want to give it, but I'm not sure whether we will be able to deal with it. Okay. Let me do their standard stuff, and if we will have time, then we will talk a little bit. Oh, or do I have problem for that? How much time do I have? Okay, yeah, I will explain this anyway, but pretty fast. So we have the complexity of n times 2 in the power of n. So to fit into this into approximately 2 seconds, n should be like 25, or no more. 25 is already big enough. However, I will tell you that I can solve this problem where n is approximately 40. How to do that? Their algorithm is named as meet in the middle. We take all these elements and split it into 2 groups. Element n over 2, and then element n over 2 plus 1, blah, 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 blah. So you have the 2 elements there. And for each this pack of elements, we calculate all the possible subsets. So we will have 2 in the power n over 2 different values here of weight and cost. So it will be weight left and cost left. And here 2 in the power, also 2 in the power n over 2 with weight r, c r. Then we want to kind of merge these 2 answers. So we have this array, 2 arrays. We have arrays of length 2 in the power n over 2 with w and c. And here is again also with the n power of 2, 2 in the power f on n over 2 with like the rights. So when it is possible to join 2 subsets from the left part and from the right part, it is possible if v left plus v right less than m. Let us sort all the possible subsets on the left. So we have w left as w left at 1, blah, 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 w left 2 in the power n over 2, c left, and it will be the corresponding cost. CL 1 blah 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 CL 2 in the power T over 2. The same here. Suppose now that we sorted them in the order of increasing W. So it is O of 2 in the power n over 2 multiplied by n over 2, because like this is n logarithm n. So it is, this is the length, 2 in the power n over 2, and the logarithm of it is n over 2. Then you just go by the weights on the right, and you just find the position where everything on the left is less than m over Wri. And we want to calculate their maximal C in this prefix. And that's it. You just go through all the possible weights here. You just try to get for all the W's on the left that are less than that we can merge together, kind of two subsets that we can merge together. And for this prefix, we should like take the maximal cost that corresponds to this prefix. Like you can do this with binary search, or you can do this in another manner, like using two pointers. Like if you sort everything on the right, then you just can go to the left here. I know that it's complicated. Yeah, I'm pretty sure that you understood almost nothing on that. But the key idea is that you just split the subset into two sets. Then you calculate all the possible subsets for the left, all the possible subsets for the right, and you want to kind of merge them together in the resulting answer. And for that, you sort left, sort right by the weight. And then when you ask with whom, like kind of we take Wri here, and all the weights that are possible to match with them are less than m minus Wri. So it is some prefix of them. Some prefix of the sorted values. And then you, out of them, you should choose their subset with their largest cost. Questions? Like you're not asked to write this algorithm in the homework. You're just like, I'm explaining you to understand that we can solve the problems using like this approach, meet in the middle, where you split the problem into two halves, like solve the problems on the left, solve the problem on the right, and then join them together. Okay. Like the complexity of that algorithm was much better than 2 in the power So let us come to the, I think, last part of today's lecture is multi-knapsack problem. So it will be even harder than the previous problem. So you know that so you have several knapsacks. Each knapsack has a capacity of n again, and you have n elements. You want to find the smallest number of knapsacks that we need to fit all their elements inside.
Oh, can I repeat?
Sorry?
May I just repeat what you said?
Yeah.
Still. So you're not saying that you have two knapsacks. You actually have a lot of knapsacks or empty.
Yeah. The question is, what is the mean? Sorry?
Sack has its and each sack has its own capacity.
No. All these knapsacks has the same capacity M. They have fixed capacity, all the knapsacks.
So that things that objects have different sizes.
Yeah, all objects, yes, they have different weights and they have different costs again.
Sorry.
So there is like n objects with the weight and the cost again. Even, do you really need costs? I think we, because we want to fit all the elements, we do not think about cost here at all. So you have n elements with their weight, and you know the capacity of the knapsacks. Each knapsack has capacity m. The question is, what is the smallest number of knapsacks we need to fit all their elements? So the reasonable thing is to take like so we have a knapsack, the first, the second, and then you want you want to add some subset of elements into third knapsack, so some subset. So, and the first idea that comes to mind is that, okay, we can possibly go over all subsets and calculate supposedly that all this subset is getting to the last knapsack. So our dp will be the following: dp mask. This is exactly the elements that we took and we didn't take. So dp mask is the minimal number of knapsacks to fit subset mask. So this will be our dynamic programming. dp of mask will be the minimal number of knapsacks that we need to fit all the elements that corresponds to this mask. Mask is just simply 0 or 1 and ones. So, how to solve this problem one by one? The best thing that we can do right now is that to take all the subsets of this mask, of this subset, so this mask, like there is the whole set S, here is the mask, and we just iterate over all the possible subsets that were in the last knapsack. So we just iterate here over mask 2. So let us calculate at first for each mask the following, like can we fit subset mask to knapsack. This will simplify our further progress. So this dynamic programming can be already calculated during the previous problem, where we should just check whether whole, like what are the subset of the element we took into the set and whether it's possible. So simply you just go over all possible masks and check whether the corresponding mask is a subset that fits into the knapsack. Then we go for mask 0, mask less than 1 over n, mask plus plus. Okay, so we have two options here. Like mask 2 equals 0, mask 2 less than 1 over n, mask 2 plus plus, if mask and mask 2 not equals to mask 2, then nothing. This check is just checks whether mask 2 is an overset of mask 2. So we check whether mask is whether mask 2 is a subset of mask. You just simply can calculate it as and comparing with mask 2. And then we just tell dp of mask equals to max dp at mask and dp mask minus mask 2 plus 1. So we just go over all the subsets of mask and we just check whether if we remove these elements from the mask itself and add 1. Okay, is it clear by now?
I have a few questions. What about fitting the sack? So we should fit it exactly as its capacity? Or
No. The capacity shouldn't exceed m.
No, not exceed, but not. It shouldn't be equal to m.
No, it shouldn't be. It should be somewhat less.
Okay, so we're going for all the subsets and they choose the optimal. And so
Sorry. Yeah, I forgot. And
we do when we do it for the first one, we take all the elements, all the objects from the pool of objects, and we do it for the second one. And the rest we just go for.
Yeah, so we should. Yeah, I agree with you. I forgot that we should if it is a subset, mask 2 is a subset of mask, and we can fit it into knapsack.
But why we choose for subset? Because we just pull it from the. Okay, we can check. I know. What about +1?
Yeah, so kind of you iterate over all the subsets of mask.
Can do this. Okay.
And you do check whether these elements can be in the last knapsack. We had some number of elements, and we can split them into the knapsacks. 1, 2, 3. Okay. So we iterate over all the subsets of these ones which are fit into knapsack. And we put them in the last knapsack. So this one is here, means that this is the last knapsack that we put down. So this is for this DP is their answer the minimal number of knapsacks for their element for all the rest elements plus 1, which are fit into the knapsack.
Okay, but can I still just generate these loops till I run out of objects? So I just go through all available subsets from the pool that are not that are still in the pool of objects, and I feed and I took the optimal subset and put it in the first stack, and delete all the objects that I choose for this stack from the pool of objects, and I build another loop, and I do the same choosing optimal subset.
Oh, you kind of you want to generate all the subsets in advance, kind of, right?
Not which we can use like combinatorics.
Yeah, like using the Python stuff that generates. Yes, yes, you can.
So I'm saying it's the same.
It's the same, yeah.
It's like first problem I didn't understand.
Yeah, it's the same. It's the same. It's just like these masks are just like the numerical representation of the set, of the subset, and nothing else.
No, I don't. I think I mean just not in one, but two objects run out.
Okay, yeah.
Thank you.
So, what is the complexity of this algorithm? It's pretty simple again. There are 2 loops.
Yes, but then I'm talking about it's a lot of loops. Because I'm like filling one side, deleting objects, running it again. Yes, I can save subsets some and then not overlap with what I've already implemented.
Oh, you can do that. Okay, that would be nice because I'm right now trying to talk about that. So the complexity here is 2n times 2n, which is equal to 2 in the power 2n.
Oh.
Which is 4n itself. So the outer loop is 2 in the power of n, the inner loop is 2 in the power of n, and thus their complexity is this one. Like right now I will explain you how to improve this complexity. Please note that for the mask tune we traversed only over the subsets, like we want to only all the sets that are subsets of mask. Only them and only them. So how to do that? We just say here mask, then mask 2 bigger than 0, no, bigger, more than 0, and mask 2 equals to mask 2 minus 1 and mask. Oh, sorry. Yeah, that's true. So this loop iterates only over the subsets of mask. This is, since we're out of time almost, I will leave you this again as an exercise for the next time to understand why this loop traverses exactly over only subsets of mask. It's pretty trivial, but like you just simply in the standard loop, you just decrement by 1. But here you just not only decrement by 1, but also take this as a end it with the mask. So like only this, take only the subset. of it.
It will be only unique subsets.
Yeah, it will be all the unique subsets. Yeah, exactly.
Thank you.
So what is the complexity of this algorithm? It becomes a little bit funnier here because each element can be of three types. Either it belongs to mask, either it doesn't belong to mask, or it belongs to mask but does not belong to, but does not belong to mask 2, and belong to mask, and belong to mask 2. So we have three options. So this will be 0, this will be 1, this will be 2. So this is for each element. You have three options. Either it doesn't belong to mask, either it belongs to mask but doesn't belong to mask 2, and either it belongs to mask and belongs to mask 2. So they're only like using ternary digit system. All 3 in the power of n different subsets can encode the pair of mask and mask 2, and they uniquely encode them. So if you do like that, the complexity will be of 3 in the power of n times times n, I think. I'm not sure. So it is faster than if you iterate over all subsets and check whether they belong. So like and the algorithm becomes simple here because we just simply if can mask, if not can mask, then 20. Okay, I think I finished for today. Do you have any questions yet about this?
As you already said, I had no one understand how to get unique
Okay.
subsets using just binary.
Yeah, using binary strings, yeah.
So when low, it's the only one.
Okay, then that's it for today. Thank you for coming, and I will send the homework in like some amount of time. Okay, see you.
Thank you.
Bye.
Thank you.
Thank you, bye.